Hello everyone, my name is Lahcen Sellak. I am PhD student from Ibnyaich University National School of Applied Science Agadir, Morocco. My study is about the design and performance improvement of a miniaturized antenna using artificial intelligence techniques. Before I start my presentation, I would like to thank the editor, associate editor, and reviewers for their comment and recommendation, which have helped us to improve the quality of our paper. I am excited to present our latest research paper accepted for publication in Telecommunication Computing Electronics and Control Journal. Untitled Artificial Neural Network Based Design of Miniaturized Circular Dual Band 4x4 MIMO Antenna for 28 and 38 GHz 5G mmWave applications. As we know, the advent of 5G technology promises previously in an undeniable speed and connectivity, making a revolution in a variety of sectors, from health to autonomous driving. However, to fully exploit the potential of 5G generation, especially in the millimeter wave spectrum, we need antennas that are not only highly efficient, but also compact and capable of achieving multi-band and good gain, and also a broad band. So based on this, our work focus on the development of a dual band 4x4 MIMO antenna for 5G application. So this presentation is organized as follow. Firstly, we begin with an introduction that covers the role of the antenna and the requirement of 5th generation technologies, as well as the theory behind the artificial neural network techniques. Next, we present the geometry of the proposed single element antenna, followed by the result and a discussion. Then the design of the proposed MIMO antenna, and finally we close the presentation with a conclusion. So the antenna is the passive component that bridges the gap between the free space and the electrical circuit in every radio systems. It serves as a crucial element converting electrical signals into electromagnetic waves from transmission and vice versa for reception. This dual functionality allows antenna to facilitate wireless communication by efficiently transmitting and receiving signals across various frequencies. So there are a lot of type of antenna, including wired antennas, dipole and monopole antennas, Yagi-Uda antenna, resonant loop planning inverted F antenna, and patch antennas. In this work, we focus on the design of a compact dual band patch antenna. So the 5G network requirement. As we know, the objectives of the 5G are to surpass the capabilities of previous generation. So to achieve this, several key requirements must be met. The first is the high data rates, ensuring faster download and upload speed to support high-definition video streaming and virtual reality. Low latency by reducing the delay in data transmission to enable real-time communication for applications such as online gaming and autonomous driving. Enhanced mobile broadband, massive machine type communication, facilitating direct internet often connectivity. So 5G operates across a broad range of frequency divided into three main bands. The first band is the lower band, or the frequency lower than 1 GHz. This band is characterized by long range and good penetration, lower data rates compared to higher band. The second band is the frequency between 1 and 6 GHz. This band is characterized by balanced range and data rate and moderate penetration capability. The last one is the height band or millimeter wave frequencies above 24 gigahertz. This band is characterized by very high data rates, limited range and penetration, high capacity, and low latency. So let's take a look at the challenge of antenna design in millimeter wave frequency. So the high frequency and as we know, if the frequency is high, the wavelength is short. So this led to high propagation loss and limited range, also and poor penetration throughout obstacle. In high frequency also, the signal is easily blocked by building and even by small objects. The height dissipation where high power density require efficient terminal management. Complexity in beamforming, while precise beamforming is required to direct signal. Also, compact antenna design needed for integration in small device, maintaining performance while reducing the size is challenging. So to overcome the challenge of this challenge, MIMO antenna is a key solution. So to design the MIMO antenna, we need first design single element antenna, and then we transform the single element antenna to a MIMO antenna. This operation involves strategic placement and spacing of multiple elements. So the correct spacing between the multiple elements is important to avoid undesirable effects like mutual coupling. So the precise modeling and design of the single element antenna before integrating it into the MIMO antenna result in a high performance MIMO antenna. Based on this, our objective in this work is to design a height isolated 4x4 MIMO antenna that resonates at 28 and 38 gigahertz. So here we present the geometry of the proposed circular patch antenna single element. As we can see, the antenna consists of a circular radiating patch with two rectangular slots inserted on the circular patch and two rectangular slots inserted in the circular patch and one circular slot also inserted in the patch. Also, we insert two notches with x0 and length of y0 between the feed line and the radiating element. In the back side of the substrate, we have the ground plane, valley ground plane, where also we insert one rectangular slot and one circular slot in order to achieve the multi-band, also to enhance the bandwidth. So our goal here is to predict the values of the dimension of various components of this antenna in order to achieve the exact desired resonance frequency, which is 28 and 38 gigahertz. Using the artificial neural network. So here we present an example of architecture of artificial neural network architecture. In general, an artificial neural network is composed of three layers: an input layer, one or more hidden layers, and output layer. This figure shows the architecture of multi-layer perceptron artificial neural network with two hidden layers. The first layer is the input layer, which contains, in this example, n neurons. The intermediate layers are the first and the second hidden layer. And the last layer is the output layer, which counts the global output of the model. So the output of the first and second hidden layer can be calculated using the equation 1 and equation 2. The global output of the network can be calculated using the equation 3. So here we present the structure of the proposed model. As we can see, the inputs are the first and second resonance frequency, F1 and F2, and H is the height of the substrate, and the output are the appropriate values of the dimension Rp, which is the radius of the patch, Rs the radius of the circular slot, Ls Ws are the length and width of the rectangular slot, LSG WSG are the length and width of the slot inserted in the ground plane. So as we can see, if we to design an artificial neural network, we need to determine the number of hidden layers, the number of neurons in each hidden layer, and appropriate learning algorithm and transfer function. So the training process was focused on optimizing the network's configuration through systematic adjustment of the number of deep layer and the number of neurons in hidden layer, and also the training algorithm. So this table shows the values of the training and testing errors for different learning algorithm. As we can see, the Bayesian regularization give minimum error, so this algorithm is appropriate for our work. So the same process used to identify the best training algorithm was used to determine the optimal transfer function for the proposed ANN model. So according to this result, the hyperbolic tangent sigmoid is the best transfer function for our problem. This function was chosen because its ability to achieve lower error, as demonstrated by this table. So here we present the error associated with varying the number of hidden layer. As it can be seen here, 2 hidden layer gave the best result. So various tests were conducted exploring diverse number of neurons in the hidden layers to determine optimal configuration for this problem. Throughout this test, it was observed that employing 30 neurons product the most favorable outcomes, as can be proved by this value of presented in this table. So here we present the final configuration of the proposed ANN models. So to test the performance of this model, we use the regression coefficient for training, validation, and testing phase. As we can see, the predicted and desired value are in good coherence, proving that our model is performant. So using the developed artificial neural network model, we predict the dimension of the antenna designed for resonance at 28 and 38 GHz. These values are presented in this table, and here the rest value of other parameter. So these values are used to simulate our antenna in a HPC simulator and CST simulator. As we can see, our antenna present resonance at exactly 28 and 38 GHz, as we can see by the reflection coefficient. Also present a bandwidth of 4.5 in the first band and 2.4 in the second band, indicating broad band and also good bandwidth. Here the VSWR, which confirm the bandwidth and also the impedance matching of our proposed antenna for the second and the first band. As we can see, the VSWR remain between 1 and 2 for the 2 respective working band. Here we present the deradiation pattern of the proposed dual band circular patch antenna. As we can see, these figures show the radiation pattern of the proposed antenna at 28 GHz and 38 GHz respectively in both the A and H planes. The proposed antenna presents good radiation characteristics in both A and H plane in 28 GHz. The antenna has bidirectional and omnidirectional radiation patterns in the H and E plane, respectively. Similarly, in 38 GHz, the antenna demonstrates nearly omnidirectional radiation patterns in both planes, indicating good performance for our proposed antenna. Here we propose the gain and efficiency versus frequency. As we can see, our antenna present max gain in the first band of 4.67 decibel and 6.7 decibel in the second band. Also, the efficiency exceeds 99%. So based on this result, the proposed single element antenna was transformed to 4x4 MIMO antenna by using 4 copies of the single element antenna arranged orthogonally in order to achieve the orthogonal polarization and also improve the isolation between the elements. And also to further explore or enhance the isolation, we use a decoupling structure composed of 4 tubes with the same length denoted as LS1 and also a cross shaped slot in the center with the length of LS2. Also in the back side we use the same decoupling structure. So here we present the reflection coefficient of our proposed MIMO antenna. As we can see, the antenna remain the same reflection coefficient of the single element antenna with bandwidth of 4.5 GHz and 2.4 GHz in the first and second band respectively. And here we present the transmission coefficient or the isolation between ports. As we can see in the first band, the isolation exceeds 23 decibels, and in the second band, the isolation exceeds 30 decibels, indicating high isolation for our proposed MIMO antenna. Here we present the VSWR for the proposed circular patch antenna, which confirm the impedance matching and bandwidth of our antenna. And here we present the degradation pattern of our proposed MIMO antenna across primary plan at frequency of 28 and 38 GHz. As we can see, the antenna shows good radiation. Sorry. So as we can see in 28 GHz, the antenna exhibits a bidirectional radiation patterns at both H and plane. Conversely, the second figure indicates that at 38 GHz, the MIMO antenna emits a predominantly omnidirectional radiation patterns in both planes. So to confirm the radiation characteristic of our proposed antenna, here we present the 3D radiation patterns. As we can see, at 28 GHz, our antenna has max gain of 6.8 decibel, and in 38 GHz, our antenna has a max gain of 7 decibel. So here we present a comparative study between our design and other design presented previously published. As we can see, our antenna has a compact size surpassing other antenna. Also has a large bandwidth 4.5 and 2.4 respectively, and a max gain of 7.3 decibels, height isolation, and also lower envelope correlation coefficient and diversity. So based on these results, we can see that artificial neural network is an efficient technique for designing multi-band antenna. The antenna proposed in this work has very compact size of 5 times 6 millimeter and has good bandwidth and height gain and height efficiency respective for 28 and 38 gigahertz respectively for the single element antenna, and also the MIMO antenna proposed in this work also offer good performance, making it desirable for 5G millimeter wave applications. So this is some references and here and thank you for your attention.